All right, while the speakers make their way to the front, hi, I'm Doug Davis, track host for this session. Obviously, we're going to be talking about eBay search on Kubernetes. A couple of things. First, there is a survey associated with each session, so please, after the session is over, please rate the presentation and, of course, the presenters. Much appreciated. And with that, now that they're here, and they're all mic'd, you're all set?
All right.
All right, hand it off to you guys.
All right, thank you. Hi, everyone. My name is Mohnish. I'm a developer with eBay's search team. And this is my colleague, Yashwanth. He's a developer with eBay's platform team, which is responsible for all things Kubernetes within eBay. And we'll walk you through a journey of how we took eBay's search use case and ran it on top of Kubernetes. So if there's nothing else that you remember from this talk, at least remember that it's possible to run a large-scale, latency-sensitive application, like a search application, and run it on the Kubernetes platform natively. And hopefully, with that said, I'll sort of walk you through what search looks like in eBay, what search's scale is, and then my partner will go into detail on what our current design looks like when we model this use case on top of Kubernetes. So let's look at search's background. eBay has its own custom search engine built in-house. It's called Cassini. It's a distributed search engine. It serves various use cases within eBay. One of the most prominent use cases is what we call as active listings. And to give you an idea, at any point in time, this search engine is serving around 1.4 billion active listings. So listings are what we call the things that you can transact on site, so buy, sell them, etc. And active is what is currently available, as opposed to there are other use cases like sold listings, which have our historical data, and you can search on the history. And so we receive around 300K QPS in one of our data centers at any given point in time in the day. Hopefully these two numbers together at least give you a rough idea that it's not possible to load all of this data on a couple of machines and be able to serve the query volume that we're talking about within the stipulated SLAs for our queries. And so, in fact, within eBay, search use case typically takes around 30 to 40% of our data center footprints. So that's how many servers, thousands of servers we are talking about. We have 5 nines of availability of SLAs that we have to maintain. Every second search is down is actually costing eBay money because users can't use our site anymore. And so a lot of our design is governed keeping this in mind, that we have to be available all the time. With that said, let's dive a little bit deeper into how eBay's search architecture looks like. So broadly, you can think of eBay's search architecture divided into 5 layers. So when a user comes into ebay.com and types in a query, USC sweatshirt, for example, it goes to our first layer, which is the software load balancer layer. These are custom inbuilt software load balancers. And as the name suggests, their job is very simple. They find the least loaded node in the downstream layer and forward the query to that particular node, which brings the query to the second layer, which is the query transformation layer. So the query transformation layer's main responsibility is to take the user's query and enhance it and annotate it. What I mean by this, eBay analyzes a lot of user data, click data that's going on, and we mine what is the demand and supply for various things. So for example, we might have noticed that people who type in USC sweatshirt are also interested and click on hoodies and tend to buy hoodies. So we will add that keyword to the original query and add hoodies, for example. We can also do spell correction at this layer, add brands, etc. to this query and transform it. And then we send this query, transform query, to the next layer is what we called as the top-level aggregators. The top-level aggregator's responsibility is to take this user query and fan it out to multiple use cases if the intent is such. So it can send the same query to our active listings and also to our sold listings. And then on the way back, it merges the results for the upstream layers to get the whole relevance and recall for that particular query. The top-level aggregators, once they fan out, send it to low-level aggregators or LLAs. They are essentially the same as the top-level aggregators, but they work within the use case. So they don't go out to multiple use cases. They work within the use case and fan the query out for the next layer. Which brings me to the most important layer, which is the 5th layer, which we call as the query serving stack. This is the layer which is essentially responsible for taking the query, running that query across the billion items that we have, figuring out the relevance of the relevance of the incoming query to the item, and then score them, rank them, and send it back upstream to the user. So this essentially is the most complex layer for us, and our idea was that if we tackle this layer correctly, other layers will take care of itself or themselves. So this is the layer that we'll be focusing this talk on. As we saw earlier, we have around 1.4 billion listings. So we cannot all fit this in the same machine, so we shard this data. So you can think of shards as columns which hold a percentage of our inventory. So or buckets rather, which hold a percentage of our inventory. And then we have replicas within the shard, or what we call rows, for handling the query volume. So essentially, the query serving stack that we have, you can think of it as a matrix with a set number of columns for sharding, and then rows for handling the query volume that we have. With that said, eBay's search use case is a little different than the traditional search use case or a web-based search use case where web pages tend to be static. Our data and inventory is changing every second. Items are getting bought, items are getting sold, prices are changing. And so what we do in our design today is we take a snapshot of the whole inventory and we ship it to this query serving grid multiple times a day. What this means is whenever the query serving grid has to load this new snapshot, it has to restart the grid while serving traffic, so that some servers have loaded the new snapshot and the rest are working its way through. Also, from the point the snapshot was taken, we continuously send all of these servers data messages that tell you the current state, because not everything is captured in the snapshot. Things are happening, and this is only happening a few times a day. So prices could be changing every second. So then we continuously keep sending it data to keep the query serving grid up to date. This factors in this complexity of shipping data and restarting the grid while serving traffic, factors in and is an important part on how we model this use case when we ran it on top of Kubernetes. So essentially, remember that the inventory that that column is serving is the state for that column, or is the state for that shard. So we looked at how search works, and it's like a search 101 for eBay. And now let's look at the Kubernetes footprint within eBay. So the team that handles all the Kubernetes clusters within eBay is called test.io. We have around 60 plus production clusters of various sizes, some ranging from hundreds of nodes to some that are in upwards of 2,000 nodes. In totality, we are handling 160,000 pods, application pods, across 30,000 bare metal machines today. And these clusters serve multiple internal and external use cases. So external use cases are things like search, which are user-facing, so you're handling that. And internal use cases is something like our Hadoop pipelines for our big data, or our AI ML pipelines, which use GPUs to create data models. So all of this today is handled by Kubernetes running within eBay. These clusters are also spread across the world into around 15 regions. What this gives applications is an opportunity to be closer to the user, closer to the edge. So some of our Kubernetes clusters are deployed on the edge, and we're using Envoy proxies and software load balancers to give them that capability. So which brings me to the why. Why did search decide to run on Kubernetes? Why can't it stay for where it is right now? So what happens is, whenever a new use case wants to onboard on top of our search engine on Cassini, it takes us a lot of time today. We go from talking to the hardware capacity team to get us the servers, to we get the nodes re-imaged to the OS we want, we deploy the software, we deploy the data. And this is the same process if we have to add capacity for, let's say, the holiday period, because we're going to go get more traffic. And so this takes time, and we wanted it such that we reduce the friction when we move on to Kubernetes. And so that was one of the main driving factors behind trying Kubernetes for search. Scale. So we saw earlier that our Kubernetes clusters are deployed to the edge, which means that if we are able to if we are able to design our workload on top of Kubernetes, it also gives eBay search to be closer to the edge by being able to run on Kubernetes. So there are lots of use cases. If you think you are typing iPhone and you see all these completions that happen, right? Those things make sense to be closer to the user, because every millisecond matters for search. Automation. So as I said, one of the main factors for search in designing is availability. We have to be available all the time, which means we lay out our grid, our topology, the matrix that we talked about, in a very specific manner. For example, when we create a column or a shard, we make sure that every single replica is not on the same rack. Just because if a rack goes down and it takes the whole shard with it, that part of the inventory essentially is invisible to the user. So it took out the whole, that chunk of the bucket basically is out. And so we cannot show the items that were in that bucket. So things like that. So what we did was we used pod affinity, anti-affinity rules that Kubernetes provides and baked this into the platform as opposed to carefully manually hand-holding how we lay out the topology. Flexibility. As we saw, search is, you can think of it as a matrix, multiple dimensional matrix. We wanted to be able to stretch it in all dimensions. So for example, when we have more traffic, you can scale it up with more replicas. When there's less traffic, you scale the replicas down. If we have more data and more inventory, we wanted to be able to expand the grid, to have more shards. And if we have less data around during the year, then we want to shrink the grid. So basically, by being on the edge and by designing our search use case on top of Kubernetes now, it allows us to achieve all of this, and which is why we tried to do this on Kubernetes and were successful. So I'll hand it over to my partner, Yashwanth, who's going to dive deeper into how our design looks like on top of Kubernetes.
Thank you, Mohnish. The first part of this journey was to convert this search application into microservices. So the first important microservice, which we call as a query serving pod. This has three major containers. The first container is a query serving container. This contains all the application logic that is required to serve the end user queries. The second container is the log exporter container. This container pushes all the application logs into our logging system. The third is a metrics exporter. This container converts all the application metrics into Prometheus format and ships to our metrics system. The second important microservice is the data distribution agent pod. The primary responsibility of this pod is to download the data onto the node. This data is used by the query serving pod to serve the user queries. We deploy this pod as a daemon set on all our K8s nodes. We also have few metric collection pods that collect both the container metrics and the node level metrics for the K8s node. We store this data on our local persistent volumes. This persistent volume is shared both by the data distribution agent pod and the query serving pod. Now, the next part of the journey is to lay out the search grid for the search use case. When we looked into the K8s ecosystem, we could not find any operator or a pattern that would help us to deploy the application in the form of a matrix. The existing patterns such as deployments and stateful sets are unidimensional. So what we did was we set out to create an operator to achieve this use case. We call this as a matrix deployment operator. So when an operator wants to deploy a search grid for a specific use case, she goes and creates a CRD for the matrix deploy. As you can see in this particular example spec, the operator wants to create a matrix with 4 columns and 3 rows. Here, columns refer to the stateful sets in the search grid, and the rows refer to the replicas for each column. This spec also has additional information like the container versions which need to be deployed, and also the data packages that need to go as part of the pod. We also track the status of this deployment grid. So once the CRD instance is created, the controller kicks in and starts creating the stateful sets. As Mohnish mentioned, the shards of each column needs to be distributed across the racks. So we use a combination of pod anti-affinity and affinity rules to achieve this kind of layout. So the stateful sets are created and the grid is formed as we just illustrated. Since the operator has asked for 4 columns and 3 rows, we create a search grid with this configuration. Now, while these pods are getting created, the service controller kicks in and creates the headless services for each of these pods. We create headless services because we want the upper level stack to be oblivious of the infrastructure changes underneath them. Now, as you can see, this design helps us to be very flexible with our search grids. It provides us the speed. For example, if we want to increase the grid size, all the operator needs to do is change the spec. It also provides us the flexibility of moving our infrastructure. For example, if you know that a specific use case is going to get more traffic while the other doesn't get that much traffic, so we can decrease the search grid for the other use case and move the infrastructure here. So it actually provides the flexibility in terms of infrastructure movement. We also monitor our search grids using the metric server. Whenever we look at the CPU and the memory utilization, and whenever it goes beyond a certain percentage, we use the pod auto-scaling capabilities to increase our grid size. Now that we have laid out the grid, the next part of the journey is to distribute the data. Since this is a stateful application, it is very important for us to maintain the right state on these pods. So we set out and wrote another operator, which we call as a file distribution operator, to distribute the data across the grid. So whenever there is new data for the use case, the data deployment orchestrator gets the grid metadata for that particular use case. This includes information like number of rows, number of columns, and so on. The orchestrator then creates the spec on the API server. For example, in this spec, we are mentioning that for shard 1, what data needs to be downloaded and where it needs to be downloaded. Once this, we also track the status of the data distribution using this spec. Things like the download speed and the progress of the download is tracked here, which is in turn used by the orchestrator for the distribution of the data. Once the CRD is created, the data distribution controller starts to push data in parallelly to all the columns in the search grid. Once the data lands on the top of the column pod, it gets replicated to its shards, which is row-based. This is done by the data distribution agent pod. Now, Mohnish mentioned that we push the data a few times in a day, as well as the incremental data to the search grid. Both these mechanisms happen through the same process. Once the data is downloaded to all the pods, we again go back to the metrics controller to actually update the spec with the latest data versions. This change in the spec is again propagated to all the stateful sets by the metrics operator. One of the problems that we ran while designing this particular grid-based application is that the same volume needs to be shared by two different pods. The solutions that Kubernetes offers today doesn't help us to solve the problem the way we intended to. In order to solve this problem, we created a mutating webhook to make sure the same PVC is shared by both the pods. Let me walk through how this goes. So the data distribution agent pod, as I mentioned earlier, is running as a daemon set on all our K8s nodes. When a query serving pod lands on that particular node, we create a PVC by binding a local PV to that particular PVC. Once this query serving pod is up and running, we go ahead and restart the data daemon set. During the restart process, the mutating webhook kicks in, and what it does is it gets the list of all the PVCs that are created on that particular node by the query serving pod. We get the PVCs and attach to the spec in the mutating webhook. So when the data distribution daemon set pod gets recreated on the node, it has a list of all the PVCs that it needs to share with the query serving pod. This is one of the solutions that we have built in order to achieve this particular grid pattern. Once we have laid out the grid pattern, the next thing we set out to do is to look at the performance of this particular application. Right out of the box, we saw a 10 to 12% degradation in the performance at around 20% CPU utilization. We wanted to be as close to our bare metal performance because this is a latency sensitive application and we cannot compromise on the performance of the application. So we set out to look at the performance of our K8s node on which the search is hosted on. So what helped us move the curve? There are three important things that helped us move the curve: the kernel, CPU, and networking. We made sure all our kernels are upgraded to the latest version on all our K8s nodes. The second factor is the CPU. We started with the CPU manager, which is a feature which is available in Kubernetes. As many of you are aware, this actually helps in better distribution of the workloads by exclusively pinning the CPUs to that workload. However, this particular change did not help us much. We then disabled the IRQ balancer on the node. This is to make sure we disable the hardware interrupts. This did not move the curve either. Then we set out to tune our P state and C state parameters to enable the turbo boost technology on the bare metal. This actually helped us move the curve significantly high. However, we were not close to the bare metal performance yet, so we wanted to get as much close as possible. We started looking into our networking on the K8s node. For normal workloads, we use OVS bridge. However, when the network packet transfer happens from the bare metal host to the pod interface, we see that there are a lot of soft IRQ interrupts happening during this process, thereby reducing the network throughput and also increasing the CPU usage. So we switched to IPv-LAN networking. This networking change reduced the number of soft IRQ interrupts, thereby increasing the network throughput on the node. So this brought us closer to the performance that we wanted to. After making these changes, we were nearly able to match the bare metal performance at around 80% CPU utilization. At 20% and 50%, we are exactly there, and at 80%, we are close to the bare metal performance. So in short, we were able to achieve the speed, flexibility of the search application without compromising much on the performance of that particular application. For the lessons learned as part of this journey, I'll hand over back to Mohnish.
Thanks, Yashwant. So Cassini is old now. It's new for us, but it's still older. So it's been around for 7-8 years that we know of. So over the years, we've accumulated a lot of tech debt. It was really difficult for us to take this monolithic application and break this down into microservices or containers and trying to figure out how the containers will communicate to each other. It was painful. It was really painful. So that's one of the things that I would suggest you start early in the design. Sorry about that. This is not a short journey for us. It's not something that will happen in a matter of few months that all of search will suddenly move on top of Kubernetes. It's a long journey that's going to take a few years. So we wanted to make sure that we minimize the disruption to our clients, our users. And so we had to do things in a way that sort of doesn't impact a lot of our clients. What I mean is we are writing metrics in the Kubernetes world in Prometheus format, but we're also writing them in the old format. We are setting our alerts on top of the Prometheus metrics, but we're also setting alerts on top of the older format, just to make sure that our tools and capabilities that we have already work. But what this also did was sort of gave us a chance to vet the old system and the new system. So we had apples and apples comparison that we could do now between both the systems. One more example is we had to develop a proxy layer, which abstracts out for our clients all of the underlying topology or the layout of the grid. Our clients code to that proxy layer using RESTful services, and this proxy layer then hides out whether search is running on bare metals or is it running on Kubernetes. So essentially, if we ever now decide to change technologies again, hopefully it causes less disruption for all of our clients, and we can just change the proxy layer and it's agnostic, and the clients above are agnostic. So we spent a lot of time developing this layer. The next one, and the most controversial one, was running the data distribution agent pod as a separate entity as part of a daemon set, as we saw, rather than as a sidecar along with all the pods, the query serving pods. This sort of brought in a lot of design changes. For example, as you saw, we had to create a mutating webhook so that we can mount the PVCs on these two separate pods now. But it was important for our teams to do it this way because the life cycles of those two things is completely separate, and they wanted to keep them separate and not intermingle them with one another if they have to do upgrades and such things. So we had to jump through hoops to basically make this work, and sort of mutating webhooks saved us there. Nodes eventually die, things go wrong. What we had naively assumed is that we are running on top of Kubernetes. If a pod dies, the stateful set will spawn it again. Not quite true. So we didn't sort of vet this design thoroughly when we started this journey. We are not using network PVCs. We are using local PVCs for performance reasons. And when a node dies, exactly when is it okay to now delete the PVC so that the stateful set can launch another pod on another node that is available? Is still something that we are working on and ironing out. So that is not something that we fully vetted when we started this journey. And of course, performance. You can never start early with performance. It took us a lot of trial and error, a lot of runs of our search grid. Hats off to our performance guys over here, sort of figuring out what works and what doesn't work. And especially for a latency sensitive application where every millisecond counts. Even though we had started early in the design that we're going to measure everything from the get-go, you can never start early enough. So yeah, that's one of the lessons learned. Future work. So this brings me what we're excited to work on next. Now that we've proved that search can run on top of Kubernetes and we've modeled our workload, you saw earlier in the slides, we have this data orchestrator layer that we use to sort of download this new snapshot of the inventory to our search grid. We also have to restart all of these nodes when the new snapshot is available. This takes time in the default strategies that are available with stateful sets when we started, because when you update the stateful set, it went pod by pod, which meant it could take tens of hours for our size of search grid to finish that just one data upgrade. So we use the data orchestrator to parallelly restart by rows. Now, in the newer versions of Kubernetes, we have this max unavailable strategy, and so we are excited to sort of try and use that and offload some of more work to the platform itself. Recently, I've also heard talks about volume cloning. So you saw earlier that whenever there is load on the search grid, we scale and bring up new pods. But the data still has to come to the new pods. And that takes time. Sometimes can take hours. So we are going to experiment and see if we can implement something around volume cloning when local PVCs are installed, such that whenever a new pod comes in, you can download this data from a peer pod rather than going across to our Hadoop clusters where the data is. Node remediation with local PVC really needs to be ironed out for us. At which piece in the node remediation workflow do we listen for an event and say, okay, the return of investment on now deleting this data is good enough that we should delete it now so that the pod can come up on another node, versus maybe a few restarts will fix it and it'll come up in a matter of seconds. So we're still going to work on ironing out that thing. As search onboards more and more on top of Kubernetes, our cluster sizes are going to grow. We have use cases that require sometimes 7,000 servers. And we want this to be more manageable. So we might have to break it into multiple clusters, which means that the controllers and operators that we write should have the ability to have this Uber view across the clusters. And so the, let's say, matrix deployment controller, or the data distribution controllers that we have, we want to add multi-cluster support to it. Not all search use cases are very latency specific. Typically for latency sensitive applications, or use cases for search, we don't share our cluster with anybody else. But not all the use cases are that sensitive, which means that we could run in a generic Kubernetes cluster, but we would still rely on some sort of pod priority or preemption, such that even when those use cases need more pods to be spawned, the other workloads that are running in the cluster can be preempted. So we haven't played with this much, but we intend to play with this in the next few months. All right, so which brings me to the end of the talk. So reiterating back, it's absolutely possible to run a latency-sensitive, large-scale application, stateful application on top of Kubernetes while keeping all of the performance or while keeping the performance as close to bare metal as possible and leveraging all the agility, flexibility that Kubernetes platforms brings. Thank you.
I think we have time for some questions. Can I get the mic turned on? Get the mic turned on. Thank you.
Have you used Elasticsearch or Solar in or any existing solutions for your search stack?
No. When we started this journey, none of those products existed in a form that they could be run on scale. So we have our own homegrown custom search engine.
And you mentioned Hadoop. So you use Hadoop behind the scenes to
yes. So the
index
data,
your data.
yeah. So the data that goes onto these nodes. So basically, the search data that it's needed to serve the relevance and calculate the relevance and all the listings. Back of the stack, we use Hadoop to create those.
That's not running on Kubernetes, I assume.
Hadoop is one of the things that is running
we are
on
running
Kubernetes.
Hadoop on Kubernetes.
Oh, so Hadoop is also part of.
Yeah.
So as I mentioned, like one of the slides we mentioned that there are some external and internal use cases. Search is an external user facing, but there's also internal use cases like Hadoop or our AI pipelines that are also running on Kubernetes now.
All right, thank you.
Sure.
Did you have a question?
Hi, thank you for the perspective. One question is, in your future plans, do you have, are you planning to move towards the service mesh architecture, or is that not so pertinent
It's
to your use
not in
case?
the immediate roadmap. It's something that we have just started talking about, but it's not immediately something that we are going to work on in the next year or so, because there's lots of migration effort from our side that needs to happen before we can start thinking about using service mesh for architecture.
So another question. So you're running Hadoop on Kubernetes, right? Are you using any operator to do that, or how like,
I wouldn't know that.
I can answer that question. So managing Hadoop within eBay is, we use custom tooling, and those tools actually manage Hadoop on top of Kubernetes. So we integrated Kubernetes API servers with that internal tool.
All right. Any other questions? Oh, here we go.
Hi. May I know what is your sharding policy? How do you actually shard your loads across?
That's a bigger, that requires a bigger answer. I can meet you off the stage for that. Yeah.
And another question is, you mentioned that your data sets are constantly updated multiple times a day or something like that, right?
Yeah.
So is there a chance of your data getting the search getting stale?
Yes, so search is an eventual consistent system. We never guarantee that you will have full consistency. So at any point in time, so let's say there are 2 snapshots of our inventory, right? We can't load that snapshot inventory in a single shot across all the servers. So at any given time, some servers will have the newer snapshot, some servers will have the older snapshot, but we are also incrementally sending it data all the time, right? So from the point that snapshot was taken to now, we are continuously sending it data. So we send data to the older servers from the older snapshot time, and for the newer servers, we send data from the newer snapshot time.
Okay, last question. What's the storage behind all of this?
For the query serving grid, it's all in memory. The data is stored in memory.
I think we have time for one more question, if there is one. No? Okay, I think that's it. Thank you guys very much. And don't forget to take the survey.
Thank you.
Thank you.
Thank you.